I have to say that I really like these models because they have some really nice features, as the previous speaker has said. In particular, they are non-parametric models, which means that the flexibility of these models grows with the number of training instances that you have observed. And they also have the nice feature that exact Bayesian inference is feasible in these models, which means that, at least for regression problems, we do not have to resort to approximate inference. And they also have the nice feature that they will output a predictive distribution, which can be used to account for the uncertainty in the decisions that you are going to make based on these models. And that's something that for some applications can also be very interesting. So let me begin with a bit of a motivation for these models. So assume that we want to solve some regression problem. We have some observed data, and what we would like to do is to make some prediction at some region of the input space in which there is no observed data point. And in order to solve this task, what we need is, of course, to use a model, right? I mean, if we want to make predictions, we need to make some assumption about the data that we have observed, and in particular that this data has been generated by some particular model. And this model may depend on some parameters, W. And of course, the simplest model that you can think of is a linear model. This model is just a linear combination of the input attributes. And essentially, what we are going to assume is that there is some target function that we want to infer from the data. And this target function has been generated like this. It's just a linear combination of the input attributes given the model parameters W. Of course, we may assume that there is some observational noise. And for simplicity, what we are going to assume is that this noise is Gaussian with some standard deviation. So the task of interest is to infer these model parameters W from the data that we have observed. In particular, the input attributes X and the target values that we have observed contaminated with noise, YI. So there are several ways to infer these parameters from the observed data, but the approach that we are going to follow here is a probabilistic approach. And in particular, what we will be interested in is in computing this posterior distribution of the model parameters W given the data that we have observed. And for that, we can use Bayes' rule. And in Bayes' rule, essentially what we have to do is to multiply the likelihood function times a prior, and that is going to give us the unnormalized posterior. If we normalize this quantity that we have in the numerator of Bayes' rule, essentially what we end up having is the posterior. So essentially the prior is going to account for our initial belief about the potential values that the model parameters can take before observing the data. The likelihood is going to tell us how well each combination of the model parameters is going to explain the data that we have observed. And the posterior represents our updated belief about the potential values that these parameters may take after observing the data. And what we have in the denominator in Bayes' rule is just a normalization constant, which is often called the marginal likelihood, because we are marginalizing the latent variables in our model, which in this case are the coefficients of the linear model. So we are going to consider in this case a very simple prior distribution for the model parameters. In particular, we're going to set this distribution to be a Gaussian with a zero mean and the identity function as the covariance matrix. So essentially, probably you are all familiar with the Gaussian distribution, but I'm going to show here some pictures about how this density looks like. Essentially, we have two parameters, the mean and the covariance matrix. The mean describes the location in the input space of this distribution, where is the center of mass. And the covariance matrix contains in the diagonal the variances of each attribute. And in the elements that are outside of the diagonal, we have covariances that will account for dependencies. So essentially, if the covariances are positive, we have a positive correlation, which means that if one attribute is large, the other attribute is expected to be large. And these covariances can also be negative. In that case, we have negative correlations, which means that if one attribute is large, the other attribute is supposed to be small. And in this case, we are going to assume the simplest Gaussian distribution, which is going to be centered at 0. And we are going to have the identity matrix acts the covariance matrix. We are going to assume independence among the components. And essentially what we have here is just a normalization constant, and the PDF of the multivariate Gaussian distribution has essentially a second order polynomial in the exponent. Okay, so this is the prior that we are going to consider, and because we are assuming that the noise is Gaussian, then the likelihood is going to be Gaussian, right? With some variance that is going to be given by the variance of the noise. The nice thing about this model is that because the prior is Gaussian, the likelihood is Gaussian, then the prior times the likelihood is another Gaussian distribution, which is the posterior, which is given by some parameters that are given by this expression. I'm not going to go into the details about how to obtain these parameters, but essentially it's kind of easy to see that the posterior is Gaussian because the Gaussian is closed under the product operation, which means that a Gaussian times another Gaussian is also Gaussian, although no longer normalized. So essentially this is the mean of the posterior, and this is the covariance matrix, which is given by this expression. So essentially, if you take a look, the covariance matrix will depend on dot products between the data, the input attributes that we have observed. And the marginal likelihood, which is this denominator that we have in Bayes' rule, it's also Gaussian in this case, and it's given by this other expression. So this is how this model looks like in practice. So before observing the data, when we don't have any data observed, the only thing that we have is the prior, right? So essentially, in our case, the prior is this standard Gaussian distribution, which has these level curves. And if we generate coefficients from this prior distribution, we will obtain lines in the space that will look like this. And after observing one data point, we will have one likelihood factor, and the posterior is going to be this likelihood factor times the prior. So if we compute the product of this likelihood factor times the prior, we end up having this posterior distribution that appears here. And essentially, the likelihood factor is just a Gaussian centered at a linear projection of the the data that we have observed. And if we generate coefficients from this updated posterior distribution and plot the corresponding lines that we have, we will see something like this. So essentially, we can see that the lines that are generated from this posterior are compatible with the data that we have observed. We have this data point. We know that the latent function has to be near this point that we have observed, but we don't really know that much, right? Because we only have observed one data point. We can repeat this process, assume that we have observed another data point from some particular linear model. In this case, this white cross that appears here are the true coefficients of the model that are used to generate the data. This is the likelihood factor of the second data point that we have observed, this one that appears here. And this is the updated posterior distribution. So now the posterior distribution is the prior, which is this standard Gaussian, times these two likelihood factors. And if we generate coefficients from this posterior distribution and plot the corresponding lines, we will observe something like this. So you can see here that the model is capturing what lines are compatible with the data that we have observed. We can repeat this process, collecting more data, and the posterior becomes more and more peaked as we have more evidence about what are the values of the actual coefficients of the linear model that have been used to generate the data. And if we generate coefficients from this posterior distribution and plot the corresponding lines, we will observe something like this. So summing up, we can observe here that the posterior captures these linear models that are compatible with the data that we have observed. And typically what you expect is that the posterior has high probability mass in regions of the input space in which the actual coefficients of the linear model that has been used to generate the data lies. Okay, so having this posterior distribution, what we can do is we can use this posterior for making predictions, right? For the targets associated to a new data point that we haven't observed. And in order to compute this predictive distribution, we simply have to marginalize the latent variables of our model, in this case the coefficients of the linear model. And we have to multiply this posterior times the likelihood factor associated to a new test point. So essentially this is going to be a Gaussian with some variance given by the noise, and it's going to be centered at W times X star. This is our posterior distribution, which is Gaussian, and because the likelihood is Gaussian and the posterior is Gaussian, then we can compute this predictive distribution in closed form. I'm not going to go into the details about how to compute the parameters of the posterior distribution, but essentially because the Gaussian distribution is closed under the product operation, we know, well, essentially this is going to be the convolution of two Gaussians, which is also Gaussian, and it's given by this expression. We can plot this predictive distribution, assuming that we have observed these 3 points that are here. And this predictive distribution is characterized by the predictive mean and some standard deviation, right? And if we plot the mean and the standard deviation, we will obtain the following level curves. And what we can see is that the model, what it's doing is doing some sort of an average of all the linear, the linear coefficients that are compatible with the data that we have observed. And the average of the predictions is given by this red line, and the standard deviation, well, the uncertainty that you have in your predictions, which is given by this quantity that appears here, is described by this dotted blue line. So you can see here that as we move away from the data that we have observed, uncertainty increases, right? And in regions of the input space in which we are close to the data that we have observed, the uncertainty tends to be smaller. So this is some nice property because it shows that, our model is able to know the things that it doesn't know, right? So in this region of the input space, probably uncertainty is large because there are many lines that are compatible with the data that we have observed. And with only 3 data points, you cannot say that many things about the actual values of the model coefficients that have been used to generate the observed data, right? Okay. So I forgot to mention it, but if you have any question, please feel free to interrupt at any moment. Okay, so of course, linear models are a bit limited, and in practice, the world is complicated, and ideally, what we would like to do is to capture complex patterns in the data that we have observed. So typically, what we would like to have is a model that is nonlinear, and that's very easy to do in the model that I have described. In particular, you only have to do some feature expansion in the input space, and instead of working with the observed attributes X, what you can do is to work with some feature expansion that is nonlinear. And for example, we may use this polynomial feature expansion that appears here until some order in particular. And again, we can solve nonlinear problems if we are using this feature expansion, right? For example, the linear model cannot capture this data that appears here. And if we use a polynomial feature expansion of up to the 2nd order, for example, we can provide a better fit of the observed data. So this is just an example of a potential feature expansion that can be used to describe the data that we have observed, but in principle, we could use any other nonlinear feature expansion. So if we do that, then the model that we are assuming, in this case, is given by this expression. We have, again, this dot product between the observed data and the model parameters W. But in this case, the dot product takes into account this feature expansion that we are going to consider. And again, the observational noise is assumed to be Gaussian with some variance. If we do that, then it's still possible to compute this posterior distribution and this predictive distribution in the same way as we did before. The only thing is that now what we have to do is to work with this feature expansion that we have described before, and in particular a matrix of the observed data in which we are no longer working with the actual attributes X that we have observed, but the feature expansion. And the combinations are essentially the same as we did before. So again, what happens in this case is that all combinations are tractable. We end up having Gaussian distributions, and we can use that to compute the posterior and also the predictive distribution of our model. And this is how the predictive distribution looks like. Assume that we have some target function that we want to describe, which is given by this red line that appears here. Sorry, the green line that appears here. And assume that we have observed just a single observation, which is given by this data point. So what we can do is we can compute the posterior for the model parameters W, and given the posterior, we can compute the predictive distribution, which is given by this Gaussian, which is characterized by some predictive mean, which is shown in red here, and some standard deviation, which is shown in this shade region of the input space. If we have more data, we can update our posterior and also our predictive distribution. And if you take a look, the uncertainty becomes smaller in regions of the input space in which we have observed data. And in regions of the input space in which there is no data observed, typically the predictive uncertainty will be large. So again, we can update the predictive distribution and the posterior as we collect more data. And if we have these two observations here, then you can see that the predictive uncertainty is being reduced. In particular, we have more evidence about the potential values that the target function may take in that region of the input space. So the predictive uncertainty shrinks. So what it's going to happen is something similar to what it's shown here. So typically you will have your prior, okay? And by incorporating likelihood factors, what happens is that you are somehow accounting for the values of the model coefficients that are compatible with the data that you have observed. So for example, before observing the data, you have this prior distribution, which is the standard Gaussian. And as soon as you observe this data point, what happens is that now there are only a few values of the model coefficients that are compatible with this data point, right? Because, I mean, if we have observed this data, the model coefficients should be compatible with, with functions that appear near this data point, right? For example, the function cannot take a value that it's in this region of the y-axis, right? Because it's not compatible with this data point that we have observed. And as we are observing more data, we will be updating our posterior by incorporating more likelihood factors. So essentially, by incorporating the likelihood and combining the likelihood with the prior, we are somehow capturing what values of the model coefficients are compatible with the data that we have observed. And then when computing the predictive distribution, which is given by this expression, if you take a look, essentially what we are doing here, we are somehow taking into account all the potential values for the model coefficients weighted by the posterior, which means that we will consider an infinite number of model parameters for prediction, but with a weight that is going to be given by this posterior distribution, okay? And what happens in practice is that that has an effect in the potential target values that we may assign to the point that we want to predict. So in the nonlinear case, essentially what is happening is the similar thing, but in this extended feature space. And what happens here is that before observing the data, there are many potential values of the model coefficients that are compatible with functions that go through this region of the input space, and that is reflected by the reflected in the predictive distribution. But as we have observations, then there are only a few values of the model coefficients that are compatible with the data that we have observed, and that is reflected by the predictive distribution. It's captured by the posterior, and it's also reflected in the predictive distribution. But in regions of the input space in which there is no data observed, we cannot say that much about the actual function that has been used to generate the observed data, right? So that's why uncertainty in those regions of the input space is typically high. And again, what we can do is we can collect more data and update our beliefs about the potential values of the linear model and also about the predictive distribution. And somehow this shows that in this case, the predictions of the model are actually quite compatible with the true latent function, which is the green line that appears here. So summing up, what happens is that this predictive distribution has a really nice feature that is able to tell us what our model doesn't know. And that's something that is really interesting for some particular applications, and it's something that you automatically get by following this Bayesian approach, okay? Okay, so having said this about this linear model in this extended feature space, I would like to point out that another way of reaching similar results to the one that we have obtained so far, in particular having this Gaussian predictive distribution, is possible by doing inference instead of in the space of attributes of our model. We can do inference in the space of functions. So before we had this prior distribution for the model parameters, W, and these likelihood factors. We combine the prior with the likelihood, and we obtain this posterior, which is Gaussian. And if you think about this prior distribution for the model coefficients is going to generate functions, right? I mean, if we generate coefficients from our prior and then plot the corresponding functions, we will obtain something like this using this nonlinear feature expansion. And if we compute the posterior and we generate model coefficients from this posterior, those are coefficients that are compatible with the data that we have observed, we will obtain this posterior distribution of, well, these functions that are compatible with the data that we have observed. So if you think about this prior distribution of the model parameters, W is going to generate a prior distribution over functions. And the same is going to happen with the posterior. This posterior distribution is going to generate a distribution of functions that are compatible with the data that we have observed. Okay, so it turns out that these random functions that we have seen before, the ones that are generated from the prior and the ones that are generated from the posterior, are samples from something that we are going to call a Gaussian process. Okay, so essentially a Gaussian process can be understood as a probability distribution over functions, so that if you choose a finite amount of input locations, x1 to xn, you will obtain a multivariate Gaussian distribution. So let's say that we look at these two input locations, 3 and 4, okay? And we generate random functions from our distribution for the model parameters and look at the values that these functions take at these two input locations. We end up having a multivariate Gaussian distribution, okay? And the nice thing is that it's kind of easy to see this, right? Because if W follows a Gaussian distribution, X times W is a linear combination of Gaussian variables, right? Which means that W times X is going to follow a Gaussian distribution. So that's for the prior, because the prior is Gaussian, but it's also true for the posterior, right? Because the posterior is also Gaussian. So summing up, we will have this property that, I mean, if we look at the values of the function, either on the prior or the posterior, at a finite amount of input locations, we will end up having this property. Okay, so
like how do you make sure that the Gaussian process functions are actually somehow related to this phi?
okay, so the main assumption that you are making is this one. So the latent function is given by this expression, is the dot product between W times phi of x, okay? And if you think about F is just a linear combination of W times phi of x, right? And if W is Gaussian, phi of x is going to be fixed. It's just a constant, right? Each component in this vector, phi of x, is going to be a constant. So you will have a Gaussian for each component of W times a constant, okay? And the sum of Gaussian variables that are independent, because we are assuming this, well, this standard Gaussian prior for W, a linear combination of Gaussian variables is going to follow a Gaussian distribution, okay? Although the values of the function need not be independent, okay? So it's true that they will follow a Gaussian distribution, but there will be covariances within this Gaussian distribution.
My intuition is that the x's and their polynomials, then they will kind of diverge.
Not really, because x is fixed, okay? So think that this this is going to be fixed. Okay. Yeah, it's true. Okay. So the thing is that. Yeah. The thing is that here I am not using this polynomial feature expansion. Okay, I am using another feature expansion. The thing is that the feature expansion can be anything that you want. Okay, and in this plot I am not using the polynomial feature expansion. But yeah, if you plot the random functions that are generated by the polynomial feature expansion, probably they will look a bit different than the ones that I have plotted here. But the thing is that you have freedom to choose any nonlinear feature expansion. Okay. What we have seen is that we have this property that the values of the function at a finite amount of locations follow this multivariate Gaussian distribution. And this is going to enable us to do inference in the space of functions rather instead of doing inference in the space of attributes. And that has some advantages. In particular, we are going to see that we can compute the predictive distribution without having to compute the posterior, right? We can directly compute the predictive distribution. And we don't need this intermediate step of computing the posterior for W and then using the posterior to compute the predictive distribution. And because of this Gaussian form, well, this shape of the distribution of the function values at finite input locations, there are going to be many closed form expressions that we can use to answer questions about the data. And if we use this, well, we carry out inference in the space of functions. Essentially, all the computations are going to be dependent on this dot product between the extended feature expansion that we have computed on the input points. Okay, this means that we don't really need to compute the feature expansion in practice. We just need to evaluate the dot product between the points in the extended feature space. And it is going to allow us to use any sort of feature expansion, even feature expansions that may have an infinite number of components. And the thing is that if that is the case, if we use a feature expansion that has an infinite number of components, the result is going to be a non-parametric model. Okay? That means that the flexibility of our model is not going to be fixed, and the complexity of the model is going to grow with the number of points that we have observed. And that's a really nice features because the world is complicated, it depends on very complex patterns, and ideally we want flexibility to capture these patterns. Okay, so this is an advantage of doing inference in the function space, and it's essentially what we are going to do in the rest of the talk. Okay, so we have this property that the values of the function at different input locations follow a Gaussian, right? And if the assumption is that the function that we are modeling is smooth, typically what we expect is that the values of the functions that are associated to points that are close one to another in the input space, they should be correlated, right? Because we expect the function to be smooth. There cannot be large changes in the function if the 2 points in the input space are close one to another. Okay, so essentially we will have this property that the target values, the y's, are going to follow a Gaussian distribution with some particular covariance metrics, and here for simplicity we are going to assume that the mean is equal to 0. And this is going to be the covariance matrix. We have these variances for each component and these covariances. Okay. So essentially assume that maybe we have observed the value of the function for one input location. Let's say that y1 is equal to 1, and we are interested in computing the potential values that y2 may take in this case. So does anyone know what is the conditional distribution of y2 given y1? What is the shape? It's Gaussian, that's it, right? So what happens is that the conditional distribution of y2 given y1 is going to be Gaussian with some mean and some covariance metrics. And the mean, it's going to be linear with respect to y1, okay, the value that we have observed. And the covariance metrics, well, the variance in this case, it's going to be independent of the value of y1 that we have observed. Okay, so assume now that the points are even closer one to another in the input space. That means that the correlations are larger, right? And we will have these level curves for the Gaussian distribution that describes the potential values associated to y1 and y2. And if we represent this in the input and output space, we will have something like this. Okay, this is the value corresponding to the function in the first input location, and the value of the function in the second input location. And if we generate samples from this distribution, what we will observe is that the two values take similar values, right? Because, well, y1 and y2 take similar values because of these high covariances that we have in the covariance matrix. Okay, so this is going to somehow indicate that the function that we expect to model is smooth, right? Because of this high level of covariances that we have between these 2 points. And if we fix one of the components, then we can use, let's say that we have observed y1. We can compute the conditional distribution for y2, and we can generate samples from this conditional distribution. And because the dependencies are very large, then y2 cannot be very different from y1, right? So by taking a look at this, you can somehow see how we can use this conditional Gaussian distribution to make predictions, right? You can think of y1 as the data that we have observed, and y2 as the data that we want to predict. And of course, this can be extended to any number of input locations because of this property that we said before, that the input locations, the values of the function at the input locations follow a multivariate Gaussian distribution. So in this case, I'm going to consider 5 input locations. And typically what we expect is that if the locations are close one to another, the correlation is high because we expect our function to be smooth. And if the input locations are far one from another, typically the correlations will be smaller, right? For example, we expect that the value of the function associated to this input location is closer to the value associated to this other input location than to this other input location, which is farther away in the input space, right? So this could be our covariance matrix for the values of the function associated to these input locations. So you think about the values of this covariance matrix, you can see that the correlations are high when the points are close one to another in the input space, and they decay as we move away from one point to another, which is the expected behavior. And I cannot plot a Gaussian distribution in 5 dimensions, but I can plot a 2-dimensional Gaussian distribution corresponding to these dimensions, 5 and 1, okay? And in this case, we can see that the correlations are not that high because y5 is a bit far away from y1, okay? So in this case, the covariances are only equal to 0.4 in this case. Later on, I will explain how to compute the entries of this matrix. That will become clear within a few slides. But now let's assume that we generate samples from this Gaussian distribution, and we plot those samples, okay? So essentially, because we have these strong dependencies between the component of the functions, what we will observe is that the values that that we will generate from this Gaussian are close one to another because of these strong dependencies that we have here. And again, what we can do is we can fix one of the components and then compute the conditional distribution of the others given this one. That is going to be a Gaussian distribution with some particular mean and some particular variance, right? In this case, I am only describing the conditional of y5 given y1 that appears here. And then we can repeat this in a higher input dimensional space, assuming that we have more input locations. In this case, I'm going to consider 20 input locations. I cannot describe the entries of the covariance matrix in that case because there are too many. It's a 20 by times 20 matrix. However, I can use a grayscale to describe the correlations and the covariances. So if the entries are black, then what we expect is that the covariances are high, and if the entries are white, then the covariances are low. And again, what we can do is we can generate samples from this multivariate Gaussian distribution, and because these covariances that we have here, what we expect is that if 2 points are close one to another, the covariances are high, and which means a high level of correlation, and similar values in the associated to the corresponding latent function. So we can generate samples again, and we may obtain something like this. And again, we can fix some of the components that, let's say that we have observed y1 and y2. We can compute what is the conditional distribution of the other components given those two. And it's going to be Gaussian. We can generate samples from those components, and we will obtain values for the function that are compatible with the values that we have observed in that case. So in this case, you can see that the dependencies between y2 and y1 are very small because they are far away in the input space. And again, you can repeat this with as many components as you want. And in this case, I'm using again this grayscale to describe the entries of the covariance matrix. You can generate samples from this distribution, and you can plot the result. And you can start to see that this begins to look like a function, right? And again, you can assume that you have observed some components, and then you can generate samples from the corresponding conditional distribution, which is going to be Gaussian, right, with some covariances. Later on, we will see how to compute those covariances. But the thing is that the conditional distribution is going to generate samples that are compatible with the observations that we have made, which in this case corresponds to some particular values assigned to some particular components of the input space. So summing up, this conditional distribution is going to be characterized by some predictive mean and some standard deviation, okay? Later on, we will see how to compute this mean and this standard deviation, but we know that the conditional is going to be Gaussian. And we can generate samples from this conditional distribution, and those are samples of the predictive distribution for the values that the function may take at different input locations, okay? Okay, so this is how the predictive distribution behaves as we observe more data. We can follow this approach, computing this conditional as we collect more data. So assume that we have some target function that we want to predict, and let's assume that we don't have any data observed so far. This is the ground truth, the red function that appears here. And before observing anything, what we have is our prior distribution that is translated into a predictive distribution with some mean and some standard deviation. And before observing the data, the mean is going to be equal to 0, and we will have some predictive variance, okay? And as we observe more data, we can update our conditional distribution, assuming the observations that we have made, using the observations that we have made. So again, what happens is that because we know what is the value of the function in this input location, the predictive variance goes to 0, and the predictive mean is updated using this conditional Gaussian. And we can repeat this process as we collect more and more data. And you can see that the predictive distribution, well, reflects what are the values that we have observed and what are the potential values of the latent function that we want to infer given the observations that we have made so far. And again, we have this behavior that in regions of the input space in which we have observations, the uncertainty is small. We more or less know what is the value of the latent function there. And in regions of the input space in which there are no observations, the uncertainty is large. We can repeat this process as we collect more data and more data. And we have this behavior that at some point we will have collected enough data to describe very accurately the target function that we want to infer. So here we have this behavior that I described before, that Gaussian processes are non-parametric models that become more flexible as we observe more and more data, okay? That's the level of flexibility of these models is not fixed beforehand. And that's something that, depending on the application, can be very interesting, in the sense that you don't really need to somehow specify the complexity of your model beforehand. So you can see this non-parametric behavior in this slide. Okay, so let me recap a bit and make a brief summary of the things that we have seen so far. You can think of a Gaussian process as a Gaussian distribution with an infinitely long mean and an infinitely big covariance matrix, okay? And typically what you expect is that the covariance matrix is going to enforce that values of the function that are located close to another in the input space will take similar values. And if they are far, they can take different values. And because of this property that we have that at a finite amount of input locations, the values that the latent function may take will follow a Gaussian distribution. Because of this property, there are many closed form expressions that we can use to answer questions about the data. And in particular, we can compute the predictive distribution very easily. It's this conditional Gaussian that we have seen before. And another thing that we have seen is that Gaussian processes are non-parametric models, which means that they become more expressive as we have more and more data. And another nice thing about Gaussian processes is that you automatically get this predictive uncertainty that is very useful to know what our model doesn't know. Particularly, the uncertainty will be high in regions of the input space in which there are no data observed. There we don't really have that much information about the potential values that the function may take. And in regions of the input space in which there is data observed, typically the predictive uncertainty will be low. And for some applications, that can be very useful. Okay, so let me follow with a proper definition of a Gaussian process. So essentially, a Gaussian process is just a collection of random variables. This collection may have infinite size. An infinite number of them will have a Gaussian distribution. There is a question there? Yeah?
I was wondering, it's implicitness of the function and bias matrix.
Yes, it will. It will. Yeah. Yeah, it will. If the covariances are larger, then you will expect a smoother function. And if the covariances are very slow, very small, typically the function will be wiggling a lot.
But it will always be continuous.
So the definition is, so basically we have described like a stochastic process in a sense. So we're going to have a random variable that has certain structure and their correlation. So the question is, is there a connection to the Brownian motion? Is it a larger class?
Brownian motion is a Gaussian process. Yeah. Yeah, it's a particular case where the covariances will have a particular shape. Okay.
With the route truth function and SME mechanism, so every time you sample a point, the response is a bit different.
Sorry, can you repeat the question? Yeah.
So here, every of your points like that on the route truth, but every time you measure at the same point, it's a bit different.
Yeah, the thing is that here we are assuming that there is no observational noise, but you can introduce observational noise very easily. We are going to see that later on. But here I am assuming that there is no noise. So because there is no noise, that's why the uncertainty goes to 0 as soon as you get an observation. If there were some noise, the uncertainty will be reduced, but it will not be exactly equal to 0 after collecting an observation. Okay, so we have this definition of a Gaussian process. It's just a collection of Gaussian variables of potentially infinite size. And we have seen that a Gaussian distribution is specified in terms of a mean vector and a covariance matrix. And what happens is that a Gaussian process is also specified in terms of a mean function and a covariance function that can be used to compute the entries of the covariance matrix. So essentially, if two Gaussian processes have the same mean and the same covariance function, then they cannot be distinguished one from another. Okay, so let's take a look at the mean function of the GP. Essentially, the mean function of the GP is going to give us the expected value of the latent function at a particular input location. And it's going to define the global tendency that the latent function will follow before observing the data. And in most practical applications, it will be simply set to 0. The reason is that the posterior mean will not be different from 0, even though the prior mean is equal to 0. And if you make inference about the prior mean, it is possible to show that you end up having also a Gaussian process with mean equal to 0. So in most practical applications, what happens is that you simply put the prior mean equal to 0, which is something reasonable to do, given that you have standardized your targets to have, for example, 0 mean. So these are samples from a Gaussian process with 0 mean. And let's say that you have some prior knowledge about the particular features of the target function that you want to infer, and you have some knowledge that it follows a linear trend. Then you can incorporate that belief into your prior mean. For example, if we have a prior mean that is equal to this identity function, and you generate samples from the corresponding GP, you will obtain something like this. Okay. You can also introduce other type of prior knowledge. For example, maybe you know that there is some trend that is periodic. You can introduce that into the prior mean. You can generate samples from the corresponding Gaussian process. For that, you only have to select a finite amount of input locations, compute the mean and covariances, generate samples from that Gaussian, and you will end up having something like this. And essentially, if you have any prior knowledge about your, let's say, the tendency of the function that you want to infer, you can introduce that into the prior mean. And if not, you can just set the prior mean equal to 0, which often works very well in practice. So another key function of Gaussian processes is the covariance function. Essentially, we are going to use the covariance function to compute the entries of the covariance matrix that we are going to use to compute the predictive distribution. So essentially, the covariance function is going to compute these covariances, and it's going to be a function that will receive 2 input points as the inputs to the covariance function, and it's going to return these covariances that appear here. And the covariance function is going to determine global properties also of the latent function that we want to infer before observing the data. So it's also another sort of prior knowledge that we can introduce into our model. For example, let's say that we assume some particular level of smoothness in our target function that we want to infer. We can introduce that into the covariance function that will generate covariance matrices that look like this. So if the points are close one to another, the covariances are going to be large, and if they are far from one from another, the covariances will be small. We generate samples from this covariance function simply by selecting a finite amount of points and then sampling from a Gaussian distribution. We will end up having something like this. But if we believe that the function is smoother, then we can introduce that prior knowledge into the covariance function. In this case, the covariances will be larger among points. Independently, well, I mean, if they are far away, the covariance will be reduced, but not that much as before. And the result is that the samples that we will get from the GP will be smoother. So if you have some prior knowledge that your function is smooth, you can introduce that knowledge into the covariance function. Or maybe your function is wiggling a lot, and you can also specify that into the covariance function. Then the entries that you will compute in the covariance matrix are going to look like this. We will have strong correlations between points that are close one to another, but very small when the points are far one from another. And that is translated into the function wiggling a lot. Or maybe there are periodicities in your function that you want to predict, okay? You can also introduce that into the covariance function, and the corresponding covariance matrix will look like this. And if you generate samples from the latent function, the samples will look like this. And they will have these periodicities that you have introduced, in the sense that the covariances will be higher between points when they are the distance from one to another is close to the period. Okay, so we have seen that a Gaussian process can be seen as well, something that depends on functions. In particular, the function, we have a function for the mean and a function for the covariance matrix. For the covariances that can be used to compute the entries of the covariance matrix. So it seems that it's a bit difficult to work with this in computers, right? Because of this infinite size. However, in practice, what happens is that what we will have to do is to work with finite amount of points that will correspond to either the training points that we have observed or the points at which we want to compute predictions. And we can use this property of the Gaussian distribution, that the marginals of a Gaussian distribution are also Gaussian, okay? So if we have different input locations at which we are interested about the potential values of the latent function, if we focus, for example, on the input locations corresponding to the training points, we know that the marginal distribution of the latent function values at those points is also going to be Gaussian, with some mean and some covariance matrix that can be obtained using the mean function and the covariance function. So summing up, we will only need to work with a finite amount of points when doing inference with Gaussian processes. And those points will correspond to either the observed data, the training data, or the test points at which we are interested in making predictions. Okay, so now let's take a look at how to compute this conditional Gaussian distribution, which can be used for making predictions. So we know that the conditional is Gaussian, but what are the parameters of this Gaussian? So assume that we have some observed data, these y2 values, those are the training points, and we are interested in making predictions at some test points, which are going to be these y1 points that appear here. So because of this property that the values of the function at different input locations follow a Gaussian distribution with some mean and some covariance, given by the mean function and the covariance function, we know that the joint distribution of these two variables is going to be Gaussian. With this particular mean, these particular covariances that appear here, okay? And these entries can be computed in terms of the prior mean and the covariance function that we have specified beforehand. So we can compute this conditional distribution using Bayes' rule, and before we saw that this conditional is Gaussian, okay? And the parameters of this Gaussian are given by this expression. This is the conditional mean, and this is the conditional covariance. So what we can see again is that the predictive mean is linear in terms of the values that we have observed. So the conditional values that we have observed, y2, will appear here. And the covariances do not depend on y2, okay? And another thing that we can see here is that typically the predictive mean is going to be more confident, the variance is going to be smaller than the prior mean, essentially because we are subtracting this term that appears here from the prior covariances, which are given by this A matrix that appear here, which are essentially the prior variances for the test points. So summing up, this is the only expression that you need to make predictions with a Gaussian process. If you have your training points, then those points will correspond on some X attributes that you have observed and some target values Y2 that you have observed. So you only have to introduce here Y2, and then you can use the prior mean and the covariance function to compute the entries of this matrix that then can be used to compute the entries of this covariance matrix associated to the predictive distribution for test points. So if you take a look, the predictive distribution for test points will take into account dependencies among the predictions that you are making for the test input locations. Okay, so now assume that we have some additive Gaussian noise. Assume that we have some target function that we want to infer, and we assume that the latent function is contaminated with noise, okay? And the noise is going to be Gaussian with some particular variance, y2. Okay, so because we have a prior Gaussian process on F, if you think about that, what we are doing is we are adding some Gaussian noise to a latent function that is assumed to be generated from a Gaussian process, right? And there is this property that if you sum two variables that are Gaussian, the result is another Gaussian random variable, right? That essentially means that Y is going to be another Gaussian process with some particular mean function and some particular covariance function. And what is the covariance function of this latent function contaminated by noise? Essentially, it's the covariance function of the noiseless function f with this term that appears here. Essentially, what we do is just add some term to the diagonal of the covariance matrix. And the term that we are adding is essentially equal to the variance of the noise. So summing up, incorporating noise into a Gaussian process, observational noise is very easy. We only have to change our covariance function like this. And because we are changing the covariance function, then the predictive distribution is also going to change. But it's going to change in a very easy way, in the sense that we will only have to add this diagonal term to the prior variances. To the prior variances of the training points, and also take into account that term when computing predictions. So if you think about the previous predictive distribution, essentially we are only adding this term that appears here, and then this other term, which is the observational noise. It's the variance of the noise that we are assuming for the training data and for the test points. So essentially, we are incorporating a bit, increasing a bit the variance of our prediction, which is going to be, the increment is going to be equal to the observational noise that cannot be reduced, right? Okay, so any questions so far? No? Okay, so just take this into account, that if you want to incorporate observational noise in a GP, it's very easy. You only have to change your covariance function. Anything else remains the same. Okay, so having reached this point, let's take a look at some examples of covariance functions, right? Because we have introduced this as a key factor when doing inference with Gaussian processes. It's something that specifies some properties of your latent function, but we haven't said how this covariance function is used. And one example is the squared exponential covariance function that has this shape that appears here. It's just similar to a normalized Gaussian distribution, okay? And this covariance function has two parameters. One parameter, which is called the vertical scale, and is related to the prior variance of the function at each input location. And then another parameter, which is called typically the length scale, and it's related to the level of smoothness of this the latent functions that we are assuming in this case. And it's possible to show that if you generate functions from a Gaussian process using this covariance function, they can be differentiated an infinite number of times, the samples, which means that the samples will look very smooth. So these are some examples of latent functions generated from a Gaussian process with zero mean and the squared exponential covariance function with these two parameters. This is the amplitude parameter and this is the length scale, okay? And if we reduce the length scale, for example, now it's 0.25 instead of 0.5 of 4, what we will see is that the function is wiggling a lot, okay? Essentially, with this, we will have a faster decay of the covariances, which means that the function won't be as smooth as in this case. And if we change the length scale to this other value, we will see an intermediate value of smoothness. And then if we change the amplitude parameter, that corresponds to changing the prior variance of the samples generated by a Gaussian process with this covariance function.
I thought that it was supposed to be a scalar product that looked like a scalar product.
Yeah, the thing is that in this case, what happens is that the feature expansion that you are considering has an infinite number of dimensions. Okay, so it's somehow hidden inside this covariance function, that fact. Okay, and what happens is that it is possible to show that the dot product in this extended feature space is equal to this expression that appears here. So that's one of the nice things about Gaussian processes, that essentially you don't really need to work with the feature expansion, okay? And you can just use the covariance function that is going to compute this dot product in the extended feature space. And that allows you to use feature expansions of even infinite size. So if you are using this covariance function, you will have this non-parametric property of the GP, that it will become more expressive as you have more data and so on. There is another question there, or no? Okay. Okay, let's see. Yeah. Okay, so having reached this point, I would like to ask you to take a look at the notebook that it's available in my webpage, and try to run the first cells to see how you can sample functions from a GP, and also you can try to complete task 1, okay? So the notebook is available in my webpage, and you can download it from this link. Okay. Okay, so you should have access to the notebook, right? Okay, so this notebook is using gPyTorch. Let me see. Yeah, it's here. So you can run the notebook on Jupyter, or you can use Google Colab or whatever you want. And in this case, what we are going to use is a framework for using Gaussian processes for machine learning, which is called gPyTorch. It's a package that runs on top of PyTorch, and it allows you to use Gaussian processes very easily, and it scales to large data sets. I mean, in the sense that you can use features like GPU acceleration and so on. So we are going to see how to use Gaussian processes for regression. And the first thing that we have to do when using gPyTorch is to specify our model. And in this case, our model is going to be a class of the type exactGP. Okay? Then we will have to specify a likelihood, which can be a class of Gaussian likelihood. In this case, we are going to assume Gaussian noise. So the likelihood is going to be Gaussian. And then we also have to specify the prior mean that we are going to consider. In this case, it can be, for example, constant mean. You are assuming that the mean is constant, equal to some particular value. And then you have to specify also the covariance function that you want to use. So in this case, if we use the squared exponential covariance function, that's the RBF kernel. Okay? It's another name for the squared exponential covariance function. And typically, we will have this property that if we can compute the mean and the covariances at finite amount of points, and that is going to be a multivariate Gaussian distribution. And in gPyTorch, we can describe a multivariate Gaussian distribution by this object that appears here. Okay, so the first step is to define the class that we are going to use. And our class is going to be a GP model that is going to extend from this class that appears here. And it's going to receive as an argument in the constructor the training data and also the likelihood function that we want to use. We will specify the mean function. In this case, we are going to specify that the prior mean is equal to 0. It's a function that is always constant and equal to 0. And the covariance function is going to be the RBF covariance function, the squared exponential covariance function that we have seen before. And then we have to specify the forward method. So essentially, with the forward method, what we will be doing is doing some computations, ones that we call this model on some data. And what the forward method is going to do is going to return essentially a multivariate Gaussian distribution with the prior mean and the covariances that are specified by the covariance function. This is for training. For testing, it will compute the predictive distribution. So essentially, this is all the things that we have to do to use a GP with gPyTorch. Then we have to create the likelihood. It's going to be Gaussian likelihood with the variance equal to 0.1. We will create some data in this case, and we will plot the data. And then we can create our model, and then we can sample from the prior. And sampling from the prior is very easy. The only thing that we have to do is to let the data go through the model when the model is in training mode, and then we can sample from the corresponding Gaussian distribution. This is going to generate a multivariate Gaussian distribution. We can generate samples. Those are prior samples associated to the training points. And then we can plot those samples, and that's essentially what it appears here. So this is the observed data, and these are the samples that we have generated. Okay. So you can run these cells, and in task 1, you are asked to see what is the effect of changing some of the parameters of the covariance function. In particular, the length scale, which is this parameter that we have seen before that is related to the level of smoothness of the function. So try to change the length scale of the covariance function and try to generate again new samples simply by running the cell codes in the notebook again. And try these values that appear here. And within these values, you are asked to say what value is more likely to have generated the observed data. And also try to see what values of the covariance, well, the length scale leads to smoother functions and functions that are wiggling more. And finally, you can also run the code that appears below to see how the predictive distribution is computed. Okay? So when computing the predictive distribution, we have to set the model into evaluation mode. And we do that by calling eval that appears here. And when computing predictions, we only have to let the data go through the model. Here, we let the data go through the model. This is going to return a multivariate Gaussian distribution, but this time it's going to be the conditional distribution that we have seen before. We add the variance of the noise by letting the result go through the likelihood, and those are our predictions. and then we can compute the predictive mean and the predictive standard deviation. So in this case, you can see that the function is not that smooth. I mean, the predictive mean is not that smooth, and probably that's because the length scale is too small. Okay, so try to run these cells, try to different length scales, and see how those are reflected into the predictive distribution. Okay. So I'm going to do that here. So you can see that if you change the length scale, and the length scale is very small, when you sample functions from your prior GP, the functions are wiggling a lot, right? And let's try, for example, another value. And if we try this value, for example, the functions look smoother, right? And we can see also how the predictive distribution looks like in this case. So you can see that the prior assumptions that you are making, they have a strong impact on the predictions that you are making. For example, if the length scale is very large, then the functions are very smooth. The samples will look like this. They look like linear functions. And because you are assuming a high level of smoothness, then the model is not able to explain the variability in the observed data. And the only way to explain the variability of the observed data is by considering that as noise. Okay. Okay, so among the different values, 0.2 is the one that generates samples that looks closer to the data that we have observed in terms of the level of smoothness, and also in terms of the quality of the predictive distribution. Okay, so having reached this point, I think it's a good time to make a break and maybe have some coffee. So let's make a 15 minutes break, and after that we can continue. If you want, you can still continue playing with the notebook during the break. And essentially what we have seen in this exercise about changing the length scale and plotting the predictive distribution is that choosing the parameters of the covariance function has a strong influence in the prior belief that you are putting over the latent function, and also on the predictive distribution that you will obtain. And from the different values that we tried, it seems that 0.2 gives the best fit to the observed data in terms of the prior functions and level of smoothness, and also in terms of quality of the predictive distribution. So a key point in when using Gaussian processes is how to choose the hyperparameters that you have in your covariance function. For example, the amplitude parameter that we have seen before, and also the length scale. And ideally, if we want to be Bayesian, what we would like to do is to choose values for these hyperparameters that are compatible with the data that we have observed. And ideally, what we would like to do is to compute a posterior distribution for these hyperparameters given the data that we have observed. So typically, this posterior will give us the values for the hyperparameters that are compatible with the data that we have observed, and it will be obtained by applying Bayes' rule. Essentially, we will multiply the likelihood times the prior, and then we'll have in the denominator the integral of the numerator, just to obtain a normalization constant and obtain a valid posterior distribution. So in fact, it is possible to follow this approach, but it has some difficulties because computing the posterior distribution of the model hyperparameters is intractable with Gaussian processes. We cannot compute the exact posterior, so we will have to resort to approximate inference methods, such as those that you have already seen during the course. However, something that works very well with Gaussian processes is simply considering the likelihood of the hyperparameters. This is also known as the marginal likelihood, where we have marginalized the latent values of the process, and we have seen before that this marginal likelihood is just a multivariate Gaussian distribution, right? It's a multivariate Gaussian density given by this expression, where this is the covariance function, that the covariance matrix that we can obtain in terms of the covariance function, and this is the variance of the additive Gaussian noise, assuming that the prior mean of the GP is equal to 0. So summing up, computing this quantity is kind of easy with Gaussian processes, and we are going to see that it can be used to perform model selection. We can choose different values for the hyperparameters using this quantity, and typically by maximizing this quantity we will obtain good results, good hyperparameters that generalize well and perform well in practice, given predictive distributions with good quality. And the reason for that is that this term penalizes models that are too complicated to explain the observed data, and also models that are too simple. And for example, if we consider the length scale of the squared exponential covariance function, in this case I am plotting here the logarithm of the length scale. So if we are over here, the length scale is very, very small, and if we are over here, the length scale is very large. And what I'm plotting here is the log likelihood function that we have seen before. And what we are seeing here is the predictive distribution, how the predictive distribution changes when we change the length scale. And essentially in this region of the input space, the length scale is very small. That means that our function is wiggling a lot, and it's going to be very flexible, right? If we assume a function that is wiggling a lot before observing the data, then it's very easy to fit all the data that we have observed using that function in particular. But on the contrary, if the length scale is very large, then the functions that we are generating from the GP are very smooth, and essentially our model is very rigid. It's less flexible, and it's very simple in the sense that probably the only functions that we can explain are linear functions. So summing up, if we are over here and the length scale is very large, our model is likely to be doing underfitting. And if we are over here and the length scale is very small, our model is going to be doing overfitting very likely. We will have a very small training error, but probably the generalization error will be very bad. And in this case, it will be the case also that the generalization error is going to be bad, because we won't be able to capture patterns in the training data that can be used to generalize. And if we look at the likelihood function, we can see that it's maximum at intermediate values that appear over here, and typically those values will result in a fit of the data that looks very reasonable, and it seems to generalize very well. Okay. So summing up, it seems that the likelihood function is penalizing models that are too simple to explain the data that we have observed, and models that are too complicated. And the reason for that is that essentially if we consider these three models, we have a model that is very complicated, a model that is very simple, and this is like the best performing model. It's very easy to see that the likelihood somehow penalizes these two models that appear on the extremes by considering that it's essentially a probability distribution for data sets, right? So what I'm going to consider is that in this axis that appears here, I'm going to have these different potential target values that we may have associated to the data points that we have observed. And essentially choosing different length scales is going to result in different probability distributions for these target values that we have observed. So essentially we have a very simple model, like the one resulting by using a very large length scale that can only explain linear functions. Probably we won't be able to explain a lot of target values, right? Because we will only be able to explain target values that corresponds to linear functions. On the contrary, if we have a very complicated model, that the model, well, the length scale in this case, it's very small, and the latent function is wiggling a lot, which means that it's very flexible, it can go through a lot of points, right? And when the length scale is very small, we can explain a lot of data sets, right? And if we have something intermediate, we will have a level of smoothness that is not too large and not too small. And we can see that essentially by choosing the hyperparameter that maximizes this quantity, we'll be doing a better job at choosing the hyperparameters. In particular, yes?
Shouldn't I just rather put prior on those hyperparameters and try to marginalize them?
Yes, that's the ideal approach that typically you should follow if you are Bayesian. But the thing is that computing this posterior distribution is intractable. Okay, so it's doable, and probably this is the most robust approach. I mean, if you have a small amount of data, probably this is going to perform better. But it's intractable, and you will have to resort to approximate inference techniques. The nice thing about the considering only the likelihood is that it allows us to do some reasonable model selection without having to resort to techniques such as cross-validation, because it penalizes models that are too complicated and models that are too simple, and it's something that is tractable. We can do without having to resort to approximate inference. But yeah, it's true that ideally this is the most robust approach, and with a small amount of data, probably this will perform better. But it's more difficult and it will be more expensive. And for that, you can use other techniques that probably you have seen during the course. Okay, so assume now that this is the data set that we have observed. These are the target values that we have observed. And if we choose the model that maximizes the likelihood, we will be essentially choosing the model that appears here, right? And we will be discarding the complex model, which is this one, because essentially this model is very flexible. I can explain a lot of data sets, and essentially because the area under all these curves, it's equal to 1, because this is a proper probability distribution that has to integrate to 1, the value of the likelihood has to go down, right? And similarly, this is a very simple model. It's the linear model that can only explain a small number of data sets, and that puts a very small level of probability mass on this particular data set that lies here. So summing up, if our particular targets are located in this part of the axis, between the three models, we will choose the one that appears here. Essentially, we will discard the simple model because the likelihood value will be very small. This data, this model cannot explain the data that we have observed. And between the red and the green model, which are these two, we will choose the green model, which is this one, because it has a higher marginal likelihood. It can also explain the observed data, and it is a less complicated model, right? In the sense that if it can explain a small number of data sets, this value has to be higher, right? Because the area under the green curve and the area under the red curve are the same and equal to 1. So summing up, maximizing this quantity with respect to the hyperparameters is expected to perform well in practice, because it will penalize models that are too simple and also models that are too complicated and that are likely to lead to overfitting. And essentially you can see that here, that maximizing the likelihood gives a model that seems to perform well in practice.
Is it possible to also maximize the likelihood such that we can put a prior on the hyperparameters of the model?
Yes, so the thing is that if you have some prior knowledge that maybe you would prefer some level of smoothness for the latent function, then you can introduce that as a prior for the length scale, and then you can consider also this term when maximizing the quantity. But most of the times, simply maximizing the likelihood performs well in practice.
How would you compare this? So this is for a specific covariance function?
No, it can be used with any covariance function. I mean, the thing is that the covariance function will have some hyperparameters, which in this case are referred to as theta. And what you can do is to compute the marginal, well, the likelihood which is given by this expression. And the thing is that the entries in the covariance matrix, in this sigma matrix that appears here, will depend on the covariance function and will also depend on the hyperparameters. So summing up, you will end up having this expression that depends on the hyperparameters, and you can simply maximize that using, for example, gradient ascent, and you can do that for any covariance function.
So can you hyperparameterize over the set of possible covariance functions?
Yeah, the thing is that it's true that it can be the case that there are several covariance functions that are candidate to be used for prediction. So what you can try to do is to simply try different covariance functions and choose the one that gives you the highest likelihood. Okay, so if we go back to the notebook, there are some cells that can be used to optimize the likelihood function, well, the marginal likelihood, with respect to the model hyperparameters. So the thing is that this function is often called also the marginal likelihood because it is obtained after marginalizing the latent values of the Gaussian process associated to the training points. So in the literature, this is also known as the marginal likelihood. Okay, so if we go back to the notebook, we have some cells here that illustrate how to do that in practice using GPyTorch. So again, we have here our model. We have the prior mean, which is 0, and the squared, the covariance function. In this case, is the squared exponential covariance function with some amplitude parameter. This scale kernel is just adding this amplitude parameter. We have the forward method that computes the multivariate Gaussian distribution when the data goes through the model. We create the model here, and then we can set the model for training, and then we can have a loop, and we can optimize this criterion, which is the exact marginal likelihood, given the likelihood that we are assuming that is Gaussian and the model. So essentially, this is going to give an objective that it's equal to this expression that appears here, well, the logarithm of this expression. And you can simply maximize that with respect to the hyperparameters using your favorite optimizer. And in this case, I am going to use Salam, but you can use any other optimizer with this learning rate. And if you run this code, you will see that the optimization process goes on. Yeah, and we can see the iterations. This is the loss, the negative loss. And this is the length scale and the level of noise that has been found. So you can also tune not only the parameters of the covariance function, but also the prior variance. And then after training, you can compute the predictive distribution. And yeah, these are the results that are obtained in this case. So yeah, it seems that you will get good results, right, by optimizing the hyperparameters. And it's something that it's very easy to do, and you don't have to resort to techniques such as cross-validation, which scale poorly when you have a large number of hyperparameters. So try to run these cells in the notebook to see that you will obtain this. I will wait maybe 1 minute. Okay, and the next thing you are asked to is to compare the predictive distribution with and without optimization of the hyperparameters. And the thing is that the reason for this is to see that it is critical to choose a good predictive, a good value for the hyperparameters. For example, in the previous example, when we set the length scale equal to 0.1 or 1, we obtain this result for the predictive distribution, okay? And probably this is going to, well, give worse results than this other predictive distribution that appears here. Okay, so summing up, it is critical with Gaussian processes to choose a good covariance function and also good hyperparameters for this covariance function. And you can very easily do that by simply maximizing the marginal likelihood. Okay, so now let's take a look at some other examples of covariance functions. So we have seen the squared exponential covariance function, but in the literature there is a wide range of covariance functions that you can use to model the data that you have observed, and each one has different properties. So one of the limitations of the squared exponential covariance function is that you are assuming that the underlying function is very smooth, and sometimes that need not be the case. So an alternative to the squared exponential covariance function is the Matin covariance function, which is given by this expression, where this is some complicated function that doesn't have a closed form expression except for some particular values of the hyperparameter nu that appears here. And this is a gamma function, and L is the length scale, and R is the Euclidean distance between points. So this covariance function has some extra hyperparameter, which is nu, and nu is the number of times that the samples from the GP can be differentiated. And essentially, if nu is very large and close to infinity, you obtain the squared exponential covariance function, and if it is small, typically you will assume that your function is not that smooth. So for example, this is with an intermediate level of mu, and this is how the covariance matrix looks like, and this is how the samples generated by this covariance function look like. And you can see that the samples are not as smooth as with the squared exponential covariance function. This is how the conditional distribution looks like, and it's characterized by this predictive mean and this predictive variance. So summing up, if you have some prior knowledge that maybe your function is not that smooth, probably the Matin covariance function is going to perform better than the squared exponential covariance function. And it's also a very popular covariance function that is used for regression, with alongside with the squared exponential covariance function. Another covariance function that it's probably not very interesting, but it's a bit relevant, is this one, which is called the neural network covariance function. And the thing is that if you think about a neural network with one hidden layer, and with Gaussian weights in the hidden layer, with some covariances, sigma squared, and some activation functions that are given by the error function, then it is possible to show that when the number of units in that neural network tends to infinity, you will obtain, as a result, a distribution over functions, that it's a Gaussian process, with this particular covariance function, where this is the arcsine function. So it's an interesting covariance function because it's a particular case of a limiting neural network with a number of units in the hidden layer tending to infinity. And it's also interesting because it's a particular example of a covariance function that is not stationary. So the covariance functions that we have seen before only depended on the distance between the points, which means that the level of smoothness of the latent function is assumed to be the same across all the input domain. And sometimes that need not be the case. It can be the case that maybe the function is wiggling more in some regions of the input space, and it is smoother in some other regions of the input space. And that can be seen here when using this covariance function. But here we can see that in this region of the input space, the function is more smoother, and also in this region of the input space, but in this region of the input space, the dependencies are smaller, which means that the level of smoothness is also going to be smaller. And you can also see that in the samples, that in this region of the input space, the samples are less smooth than in this region and this other region. So yeah, that's also another interesting property of covariance functions, that sometimes they are stationary, and if the stationary hypothesis is fine, you are happy with that, but sometimes it's a good idea maybe to consider a covariance function that it need not be stationary. This is how the conditional distribution looks like, and the predictive distribution is characterized by some mean and some standard deviation. And sometimes it can be the case that you have some prior belief that maybe your covariance function has some periodicities, and if that is the case, you can use a periodic covariance function. So this is an example of a periodic covariance function with some length scale parameter and also some period parameter. When using this covariance function, typically what you will expect is that the function will take similar values when the distance between the points is similar to the period. And if you use this covariance function, you will obtain this covariance matrix, and that means that the dependencies will increase as soon as the distance approaches to the period. And when you generate samples, you can also see that there are some periodicities that appears in the latent function. So summing up, if you have some prior belief that your latent function has some periodicity, then you can use this covariance function to introduce that prior knowledge into the inference process. This is how the conditional distribution looks like, and the conditional samples with this predictive mean and this predictive standard deviation. And another particular case that could be interesting is the Ostein-Uhlenbeck covariance function. This is a particular case of the Maten covariance function that we have seen before, when the new parameter is equal to 0.5. When the new parameter is equal to 0.5, the samples that you will obtain from the GP, they cannot be differentiated. So typically they will not be very smooth. However, this covariance function is interesting because it's the only one that results into a Markov process. It's the only Gaussian process that has the Markov property, which means that if you have observed this axis is time, and if you have observed the process values until some point, what the process does in the future only depends on the actual value at the last observation, not on the previous observations. So that's an interesting property, and yeah, maybe this covariance function is interesting for that reason. This is how the conditional samples look like, and the predictive distribution. And another example of a covariance function that could be interesting is the linear covariance function. So this case is just given by the dot product between the input points, and we have some parameters like the variance associated to the bias of the linear, the variance associated to the parameters of the linear coefficients, and also this parameter C, which is related to where the lines will cross one of the axes. And if you generate samples from this Gaussian process with this covariance function, you will observe lines. And again, this is an example of a non-stationary covariance function. You can see here that the level of dependencies, the correlations will depend on the region of the input space. And you can condition on a particular point and also compute the predictive distribution. Okay, so at this point we can go back. Yes, there is a question there. Yeah? Yeah, go ahead. Yeah.
The results of that Gaussian process, are they going to be similar to the results of the linear regression that we have in the...
It's the same. Yeah, it's the same. It's exactly the same. But the thing is that in this case, we'll be doing inference in the space of functions rather than in the space of parameters, but the predictive distribution that you will end up having is exactly the same. Okay, so we can go back to the notebook and yes? Okay, sorry. Yes?
I have one more question just to get the intuition. For example, in the case of the periodic, when would I go for a periodic mean that encodes the data? When would I go for the periodic term?
That's a good question. Yeah, I guess that probably the periodic mean is a stronger assumption, because it will be reflected. The thing is that it's hard to say that, but yeah, it's true that you can introduce also periodicities in the mean and also in the covariance function. But let me think. Probably it's better to have those in the covariance function, because yeah, I think the thing is that when you are introducing periodicities in the mean, essentially you are assuming that the periodicity is within the average value of the function that are generated, and when you are introducing them in the covariance, it's in the samples that you are generating. So I'm afraid that I don't really have the answer to that, but probably it's better to do that into the covariance function. Yes?
How do
So typically for that, you need prior information about your data. So maybe there is like a strong belief that in some regions of the input space, the level of smoothness is different than in some other regions. Then probably you will be doing better by choosing something that is non-stationary. For example, let's say that your function is very smooth in one region of the input space, and then there is like a sharp transition to some other region, and then the function is very smooth. So probably that cannot be modeled very well with a stationary covariance function.
Are there any statistical tests to know it? Suppose we don't have any information.
Yeah, so something that you can always do is to use this marginal likelihood to compare different covariance functions. So to choose among different covariance functions, you can always try to see what is the marginal likelihood that you will obtain with each one, and then you will pick up the one that maximizes that quantity. And if you have a reasonable amount of training data, typically that is expected to generalize well. So that's something that you can always do. You can use the marginal likelihood to distinguish not only between hyperparameters of the covariance function, but also between different covariance functions.
Probably one more question with this Ornstein-Uhlenbeck covariance function. You mentioned that it is the only one which has Markov property. So in your experience, are there any specific use cases where you suggest that this Markov property is really useful?
I haven't used this covariance function in practice, but I guess that it can be the case that there are applications in which it is useful, but I haven't used it in practice. So I cannot say that much about it. Yes? Okay, so we can go back to the notebook, and we can complete task 2. So here what we will be doing is changing the mean function and also the covariance function to see how the things work in practice. And here we have our model, and in this case we are going to use a linear mean function and the Maten covariance function. In this case the new parameter, it's going to be equal to 0.5, and essentially what you are asked is to try to generate samples from the prior when using this prior mean function, and also this covariance function, and see how the samples look like. Okay, so maybe we can run this. We can run this, and then run again the cells corresponding to the sampling from the prior. Okay, so this is how the samples look like. And yeah, you can see that the samples are not very smooth because of this new parameter that we are using, which is equal to 0.5. And you can also see the linear tendency that we have in the prior mean. So maybe try to change this to different values. Let's see. Maybe we can set this to 0.5. Maybe change this to -2. So now the samples are a bit more smoother because we have increased the new parameter of the Maten covariance function. And also we can see this tendency that we have in the prior mean, that it's linear with a weight equal to -2 in this case. So we have this descending trend. And then we can run the cell that will compute the predictive distribution. Let's see, where is it? Yeah, okay. And you can see that the predictive distribution is slightly different by changing the prior mean and also the covariance function. And the thing is that when you are computing predictions in regions far away from the observed data, it's where the prior will have a stronger impact. Typically, what you will observe is that the predictions go back to the prior when you move away from the observed data. And that's where this prior mean will probably have a bigger impact. And yeah, okay, so maybe we can try 1.5. So ideally, the samples should look a bit less smooth now. So we can see that. And then we can plot the predictive distribution. Which in this case looks like this. Okay, good. So maybe I will, for the sake of time, maybe I will continue. And if you didn't have the time to run these cells, you can do it afterwards. So okay, so something that is also very interesting with Gaussian processes and the covariance function is that you can combine covariance functions. And in particular, you can multiply covariance functions. If you multiply two covariance functions, then the result is a valid covariance function. And that it is possible to show that that is essentially assuming that the latent function that you are inferring from the observed data is the product of two latent functions, each one corresponding to one of the covariance functions. So you can think of the product of two covariance functions as an AND operation. Essentially, what will happen is that the dependencies between the function values at 2 points will be high only if the two covariance functions provide high covariances. Okay. So, for example, we may have a covariance function that will generate this covariance matrix, another covariance function that will generate this covariance matrix, and then this is going to be the product. So if you take a look, there are only strong dependencies in this region of the input space. So let's take a particular example. We may have a linear covariance function times a periodic function. This is the covariance function. This is how the covariance matrix looks like. And this is how the samples looks like. And in this case, what we will end up having are periodic functions with a growing amplitude. This is how the conditional distribution looks like, and the predictive distribution. And another example is a linear covariance function times a linear covariance function. And if you remember from what I said before, the result is the assumption that your target function has been generated by the product of these two functions. So what happens if you multiply a linear function times another linear function? You obtain a parabola, right? A quadratic function. And that is exactly what you will get in this case. So this is how the samples will look like in this situation. Again, this is a non-stationary covariance function. And this is how the conditional distribution looks like in this case, and how the predictive distribution looks like with some particular predictive mean and some particular standard deviation. Okay, and besides multiplying covariance functions, you can also add covariance functions. So in this case, what we will obtain is again a valid covariance function, and you can think of this as an OR operation, in the sense that the covariances will be high if they are high according to one of the two covariance functions. Okay. And again, if before the assumption was that the latent function is the product of two functions, here the assumption is going to be that the latent function is the sum of two latent functions, each one corresponding to each one of the covariance functions. So an example is a linear covariance function plus a periodic covariance function. This is going to be the final covariance function that you would obtain. And if you generate samples from a GP with this covariance function, you will obtain periodic functions with a linear trend. Okay? And if your data has this feature, it could be the case that by using this covariance function, probably you will obtain better results. Again, in this case, we obtain a non-stationary covariance function, and this is how the conditional distribution looks like. And the predictions, the predictive mean, and the predictive standard deviation. So let me give a brief summary of the things that we have seen so far. So we have seen that covariance functions introduce strong assumptions about the nature of the latent function that you are inferring from the observed data. And if those assumptions are right, probably you are going to obtain good generalization results. And if they are bad, probably the performance is not going to be very good. In most practical situations, often when you are addressing regression problems, simply by using the squared exponential covariance function or the Maten covariance function, you will obtain good results. So those are, by default, the covariance function that most people use in practice. We can see that covariance function can be used to interpret the data. In particular, the parameters of this covariance function can be, functions can be used to interpret the data. For example, if our data has some periodicity, and we tune the period parameter of our covariance function, then that has a very clear interpretation. Also, the level of smoothness, the length scale, it's also easy to interpret, or the amplitude parameter, which is the range of variability of our function, can also be interpreted. And we have seen that we can combine covariance functions simply by summing or computing their product. And we can discriminate among the hyperparameters of the covariance function and also among different covariance functions by using the likelihood or the marginal likelihood. We can simply maximize this quantity and choose the covariance function or the hyperparameters of the covariance function that maximize this quantity. However, you have to be careful when using this approach, because if your covariance function is very flexible, it is possible to tune your prior so that it can only produce the data that you have observed. And probably that is going to lead to overfitting. But if you have a reasonable amount of data, overfitting is more difficult, and typically this performs well in practice. Because we have seen that it will try to somehow penalize models that are too complicated to explain the observed data, and also models that are too simple to explain the observed data. Okay, so again, we have some cells in the notebook to see how we can use this combination of covariance functions, and in particular how to use GPs to interpret the data that we have observed. And if you go back to the notebook, you have an example here. So let me see. Yeah, this is some data. It's a typical example of how to use Gaussian processes for prediction and also for interpretation of the data. And it's extracted from this book that appears in the references that you have at the end of the slides. So this data it's a time series. So the input attribute is time, and then we have carbon dioxide concentration at some observatory in Hawaii. And we can see how this the carbon concentration changes with respect to time, and the idea is to try to predict that, to extrapolate predictions. And before using this data for learning, we have to do some pre-processing. And this is how the data looks like. So here we have the GR, and this is the carbon concentration, okay? CO2 concentration. We can see that it's growing with time. And there is also some features in this data, right? Like some periodicity, probably because winter and summer in the North Hemisphere and so on. So there is some pre-processing of the data in which we are computing some average value across each month because we have daily data. And then we can choose some particular covariance function to explain this data. And in this case, we are going to introduce a particular covariance function that has some properties that we believe this data has, so that we can then use this covariance function for extrapolation. So, for example, there is a long-term rising trend. So if you take a look, it seems that the function is growing with respect to time. And in this case, this is going to be modeled using a simple squared exponential covariance function, although you could use other alternatives, but in this case, we are going to use this. And then there is like a seasonal variation. It's changing with respect to the season, like this. And we can introduce that periodicity by using a periodic covariance function. Okay, let me see, where is it? Yeah, periodic exponential sine square covariance function, such as the one that we have seen on the slides. And it has some parameter like the length scale and also the period that will be tuned. And there are some small irregularities that we can try to model. For that, we can simply add another covariance function. And then there is some noise, that we assume that there is some noise that may depend on the input. So we can add another covariance function with a small amplitude parameter to try to model that particular component of the target function that we want to describe. And this is the covariance function that we want to use. So you take a look, using a combination of covariance functions, it's very easy when using GPyTorch. We only have to create the covariance functions and then we can simply add them, okay? So in this case, we have the long-term trend, the seasonal covariance, some irregularities, and the extra noise that we are going to model. And then we can fit the model using our favorite optimizer for the marginal likelihood. In this case, we are going to use LBFGS. This is the fitting process of the model. And after the fitting process has been carried out, then we can try to predict, for example, in the future. And these are the predictions that we will obtain in our model. So you can see that there are some periodicities here that are captured by the periodic covariance function, and we obtain the predictive mean and also the predictive standard deviation. So we get these error bars on our prediction, which could be nice depending on the application. And then we can try to look at the parameters that we have obtained when optimizing the marginal likelihood. And in particular, pues, we can see that, yeah, what is the length scale of the long-term component of the function, also the periodic component of the function, what is the amplitude, the decay time, and so on. And we can extract all that information from the hyperparameters that we have tuned by maximizing the marginal likelihood, okay? Okay, so now you can try to run these cells again by changing the covariance function. Instead of using this flexible covariance function, we can try to see what are the results when we use the squared exponential covariance function. Okay, so let's try to do that. Well, before that, I'm going to run these cells, which I didn't. Let me see. Yeah. And then we can change this. So if we only want to include the squared exponential covariance function, what we can try to do is to simply comment this. Okay, and we will only have the long-term trend, which is given by the squared exponential covariance function. And we can try to plot what are the results in this case. Let's see if this works. Yeah, and you will get these predictions in this case, because we are only capturing the global trend. So you can see here that it's very critical to choose a good covariance function to explain your data. So in this case, we cannot capture periodicities and so on, and yeah. Okay. So yeah, maybe you can try to run this. Yes. So ideally, the more data you have, the better, because I mean, if you have more data, that is going to be very useful to discriminate among different covariance functions. And the thing is that if you have a small amount of data, it will be more difficult to discriminate among different covariance functions. And if you have a very flexible covariance function, you run the risk of overfitting, because it will be like tuning your prior to explain just exactly the data that you have observed. So you can think of a Gaussian, for example, if you have a Gaussian distribution as your hypothesis and you only have one observation, then the optimal thing to do to maximize the likelihood is to set the variance equal to 0. And that is going to give you a very high likelihood, but it's going to generalize very poorly. So it will be exactly like saying, okay, this is the only data that I can explain. So you have to use this thing of maximizing the marginal likelihood with care, because if your covariance function is very flexible and you have a small number of data points, that is going to lead to overfitting. In that situation, what you should do is to follow the full Bayesian approach and compute this posterior distribution. And this is going to be very robust, and probably it will generalize much better. But the thing is that it's intractable, you have to resort to approximate inference, and it's more complicated. The thing is that this is going to be Gaussian with respect to y, but it's non-Gaussian with respect to theta. It's a complicated function, okay? Which means that this denominator that you have here is intractable to compute. So essentially the denominator is the integral of the numerator with respect to theta. And if the dependency is complicated, for example, maybe your covariance function is complicated, you cannot compute the normalization constant, which implies that you cannot compute the posterior. Okay, so you will have to resort to approximate inference to generate, for example, I don't know, maybe you can use variational inference or Markov chain Monte Carlo techniques. There are a wide range of different methods that you can try to use to approximate this posterior distribution. Most of the times, Markov chain Monte Carlo methods are used with GPs to sample from, in an approximate way, from the posterior distribution of the hyperparameters. No, I am afraid it is not. Sorry about that. But in other frameworks that we will see at the end of the slides, it is. Okay.
In the previous example, when we only captured the long-term trend, why was the relevant one larger for observed data? Because we're not capturing the periodicity anymore.
Yeah, the thing is that yeah, it's the thing is that with the squared exponential function, you cannot capture the periodicity. And the thing is that as you move away from the data, you will try to revert to the prior. So if we didn't plot the predictions in this region of the input space, but probably we will see that this will end up going to the prior value of the function in the end. Yeah, the thing is that probably here it is not plotted the noise. The noise, so probably the noise, these variations are explained by the noise. Okay, and here we are plotting the predictive value for f, not for y. And that's why it is not shown here. So that's the nice thing about GPs, that you can make inference for y, but also for f. And in some applications, it's interesting to make predictions for the value of f, which is the noiseless function. Okay, so So sorry, can you repeat the question? So the question is about whether to incorporate the periodicity in the covariance or use the mean prior. Yeah, it's this thing that I said before, that it's difficult to say, but the nice thing is that I guess that you can always try to use the marginal likelihood to see which solution is better in terms of that, and probably make a choice. But yeah, it's difficult to say that. I have to say that I don't have that much experience modeling periodic data, so I cannot say. But most of the times, people introduce prior knowledge into the covariance function, and most of the times the prior mean is set equal to 0. So I guess it would be better to use the covariance function. Okay, so far we have seen how, yes, there is another question there.
Yes, I want to know, for instance, in generating the correlation data, that is correlated, do you have a specific way of choosing the covariance functions for it?
Yeah, it's difficult to say that. So what happens is that if you are just interested in solving regression problems, most of the times what happens is that using one of these two covariance functions will give you good results. But if you have prior knowledge about the type of data that you are modeling, and you know beforehand that there are periodicities and these things, you can try to introduce that periodic covariance function, or maybe some other type of covariance function, and you can use the marginal likelihood to discriminate among those. I mean, you can try to see what is the value of the likelihood after maximizing that with respect to the hyperparameters, and see if there is some improvement. And maybe you can try to build more complex covariance functions. In fact, there is some research work. It's been I mean, it was from several years ago, but it was called the automatic statistician. And typically that is a machine learning method that will try to build a complex covariance function by incorporating more covariance functions and using the marginal likelihood to discriminate among them. And then you will get like a report, automatic report, that will describe the data, similar to the one that we have seen in the notebook. So yeah, most of the time the thing is that if you don't have any prior knowledge, just use the squared exponential or Maten covariance function. And if you have some prior knowledge, you can try to incorporate that in the form of another covariance function. And if not, you can try to add covariance functions and use the marginal likelihood to see if there is an improvement on that. So, but I guess that this is something that is similar to any probabilistic method, that typically you will have to specify a prior. And the better the prior reflects the features of your data, the better the results that you are going to obtain. So that's another advantage of Gaussian processes, that it's kind of easy to introduce this prior knowledge, because essentially you can do this in the form of the prior over the latent function, in the form of the prior mean or the prior covariance function. Okay. So are there any other questions? Okay, so far we have seen how to address regression problems. However, in general, there are other machine learning problems that are interesting, right? And some of those problems involve predicting labels, addressing classification problems. And in order to do that, we have to slightly change the way we have done things so far. And in particular, if we want to solve a classification problem, what we are interested in is in splitting the input space in different regions in which we will predict different class labels, right? If we have, for example, k class labels, we will split the input region, the input space, in different k regions. And of course, at this point, it is natural to ask, what is the optimal rule? What class label should we assign at each different input region in order to minimize the prediction error, right? So in order to do that, what we can do is to consider the probability of making a classification error, right? So the probability of making a classification error is the probability that the data point belongs, for example, in a binary classification problem to region 1. That's the region where we will predict class label 1, and the instance comes from class label 2, right? If that is the case, we will be making an error. And we can also make an error if the instance falls in region 2 of the input space. That is the region in which we will predict class label 2, and the instance comes, in fact, from class label 1. So essentially, this is the probability of making a mistake, right? And if we look at this, it is very clear that the rule that minimizes the prediction error is the one that appears here. Essentially, if the probability that the data comes from the class label 1 is larger than the probability that the data comes from class label 2, we should predict class label 1, and the other way around, right? And essentially, because these joint probability distributions are proportional to the class posteriors, essentially we can very easily see that the optimal prediction is to assign the class label with the highest posterior probability, which seems very reasonable, right? I mean, if we have some distribution that can explain the data that we have observed, we should predict the class label with the highest posterior probability. So it is possible to show that here we have this joint probability distribution for the data instances. In this case, the data instances have only one dimension, and we have split the input space in these two regions, right? Region 1, where we will predict class label 1, and region 2, where we will predict class label 2. So if we set the decision boundary here, that means that in this region we will predict class label 2, and in this region we will predict class label 1. We will be making a mistake if, for example, the instance comes from class label 1 and falls in region 2, right? So this is the probability mass that this event occurs. So this is going to contribute to the probability of error. And again, we will make a mistake if the instance comes from class label 2 and it falls in region 1, right? So the probability that that happens is given by this area. So essentially, that is the probability of making a mistake if we place the decision boundary here. And we can see that this is not the optimal decision boundary, right? Because in fact, the optimal decision boundary is located in this region of the input space, because we will be saving this contribution to the error, okay? So summing up, what we are interested in when solving classification problems is estimating these class posterior probabilities, right? Because they are going to give us the optimal decision rule that we have to apply in that setting. So when solving a classification problem, the goal is to estimate this class posterior probability. So essentially, we'll have, if we have some binary classification problem where the class labels can be 1 and -1, what we want to infer is the probability that the instance belongs to class label 1 given the attributes that we have observed so far. And the thing is that with Gaussian processes, we have seen how to use them to solve regression problems, right? And how to make predictions when the target values fall in the real line. However, it is a bit challenging how to solve this other problem where we have to estimate these class posterior probabilities. So in practice, it's kind of easy to do that by squashing our latent function with some other function, a link function, so that the values that we will obtain fall in the interval 0 to 1. For example, we can use the indicator function to squash the latent function values to values that are either 0 or 1. Or maybe we can use the sigmoid activation function that will transform the real value that will output this latent function to some value in the interval 0, 1. Or maybe we can use a probit function, which is just the CDF of the standard Gaussian distribution. Of course, what we will be doing in this case is modeling this latent function via GP, okay? And by using this latent function and this link function, we will be able to estimate these class posterior probabilities. And the link functions, they look like this, essentially. So I'm going to plot how this squashing is done in practice. So we have here our prior latent function, which follows AGP. It can take the function can take values in the real line. And if we apply, for example, the sigmoid activation function, we will be squashing that function in the interval 0, 1, right? And that means that we can use those values as actual values for these class posterior probabilities, right? And those are the values that we will need to solve classification problems. So summing up, we can very easily do that simply by considering that the actual observations are related to those class posterior probabilities that are obtained by squashing the latent function via the link function that I have described before. Okay. So yeah, I am running a bit out of time, so I'm going to skip this. And what we would like to do in practice is to make inference about the latent function f given the class labels that we have observed, right? So what we will be having as the observed data now are the class labels y. We'll have some latent variables in our model, which are the process values associated to the training points. And what we would like to do is to compute this posterior distribution for the process values associated to the training points, given the data that we have observed, which in this case are the input attributes x and the target labels y. That can be the 1 or -1. And for that we can use Bayes' rule, as we did before. And we can use the fact that in this case the prior distribution over the process values at the training points, the latent function associated to the training points, is going to be given by AGP, which means that this prior distribution is going to be a multivariate Gaussian distribution with zero mean and some covariance matrix given by the covariance function that we have specified. And the likelihood is going to depend on the link function that we have chosen. For example, if it is the sigmoid activation function, these are going to be a bunch of factors that depend on this sigmoid function that we have described before. The problem with this is that now we cannot compute this posterior distribution. Before, the likelihood was Gaussian, the prior is Gaussian, the posterior is Gaussian. But now what happens is that the prior is Gaussian, but the likelihood is not Gaussian. It depends on this link function that is different from a Gaussian distribution. That means that the posterior is not Gaussian, and in fact, computing the posterior is intractable because we cannot compute this normalization constant that appears in the denominator. Because essentially we will have to marginalize the latent values of the function at the training points, f, and that's something that is intractable. Okay, we cannot solve that integral analytically, so we will have to resort to approximate inference. And something that we can do is to use for this, use to approximate this posterior distribution. Instead of considering the exact posterior, we can consider an approximation. And in this case, the one that I am going to consider is a very simple technique, which is called the Laplace approximation. Okay. I'm not going to go into details about how to obtain this. I'm going to show this figure. Assume that this is our target distribution that we cannot compute. We can only evaluate up to the normalization constant. Okay, and it has a complicated shape. What we can try to do is to find a mode of this distribution. We can compute the logarithm at the mode, well, the logarithm of the target distribution, and then we can do a second order Taylor approximation at that mode, okay, which is fitting a parabola at the mode. And then if we take the exponential again, we obtain a Gaussian approximation, okay? And using this Gaussian approximation, we can approximate this posterior that appears here. And that is going to give us a Gaussian distribution for the posterior values of the latent function at the training points. And then we can use that posterior approximation for making predictions. Let me see. Yeah, it's here. So this is the approximate predicted distribution that we will obtain. This is the approximate posterior of the process values at the training points. if we want to make predictions at a new test point, we can use this conditional distribution. This is essentially a conditional Gaussian. It's this conditional Gaussian distribution that we have seen before. And this is the probability of having as label y star as to the new test point x star. Okay? So summing up, this is Gaussian, this is Gaussian, this is also Gaussian, and the result is a Gaussian distribution after marginalizing this variable that appears here. And then we only have to solve this integral, which is a one-dimensional integral, which is easy to solve. But here we can use, for example, quadrature for that. So these are the parameters of the predictive distribution that we will have in this case. And then we can compute predictions for new data points. So this is how the predictive distribution will look like. This is some positive points, negative points. In green, you have the optimal decision boundary. And in black, you have the decision boundary that it's inferred by the Gaussian process. And the nice thing is that you will get the posterior probability for each class label. And again, you will have this behavior that the uncertainty increases in regions of the input space that is far from the observed data. For example, you can see that in this region of the input space, the probability of assigning class label blue is smaller than in this region of the input space. Okay? So again, you will have this behavior that when you move away from the observed data, uncertainty will increase, which is something nice that it's typical from Gaussian processes. Okay, so just to conclude, mention that you have an example here at the end of the notebook where you can run some code to reproduce these experiments using the Laplace approximation. And you can plot the decision boundaries that you will obtain and the class probabilities. So in this case, we have this non-linearly separable classification problem with two classes. And these are the posterior class probabilities that you could obtain using the Laplace approximation. Okay, so I'm going to skip some slides here, and I'm going to conclude giving a bit of a summary of the things that we have seen so far. So we have seen that a Gaussian process can be understood as a Gaussian distribution with an infinite long mean and infinite covariance matrix of infinite size. We have seen that Gaussian processes are non-parametric models that become more expressive as we have more data, and they can also be useful for interpretation. In particular, the specific parameters of the covariance function have some meaning, like the amplitude of the function, the level of smoothness, the periodicity, and so on. And the nice thing about Gaussian processes is that you get this predictive uncertainty in an automatic way. And typically, this uncertainty is high in regions of the input space in which there is no observed data, and low in regions of the input space with observed data instances. And for some applications, this predictive uncertainty can be very useful. We have seen that we can perform model selection with Gaussian processes simply by maximizing the marginal likelihood. In regression problems, we have a closed form expression for that quantity, and we can compute gradients and optimize that value with respect to the hyperparameters. And typically, that is going to penalize models that are too simple and models that are too complex to explain the observed data. So in practice, it is expected to give models that will generalize good. And we have seen that we can also use Gaussian processes to address classification problems. But in that case, we have to resort to approximate inference because the posterior is no longer Gaussian, it's intractable, and we have to use some technique to approximate the posterior. In this case, we have seen the Laplace approximation, but there are other approximate methods that can be used for computing the posterior in that case. So thank you very much for your attention. And if you have some questions about Gaussian processes, I will try to answer that now within these last 5 minutes. Yeah, the thing is that in high-dimensional spaces, it's more difficult to solve a learning problem. I mean, it's not something that is specific with Gaussian processes, but it's more challenging with any machine learning algorithm because of the dimensionality, that the space is almost empty. And then when you want to make decisions, then there is like less data available to infer things. But it will depend on the main assumptions that you are making. For example, if your function is very simple, I mean, let's say that you have a very high dimensional space, but your function is really simple, let's say that it's linear, then it can be the case that you will still get good results. And I haven't mentioned it, but there is some nice feature about Gaussian processes and the squared exponential covariance function, which has this length scale. Let me see, where is it? Yeah, we have this length scale hyperparameter in the squared exponential covariance function. And the thing is that you can have a different length scale per input dimension. And if there are some dimensions that are not relevant for prediction, if you optimize the marginal likelihood, what you will observe is that some of these length scales, they become very, very large, okay? And if that is the case, it's equivalent to saying that that dimension is irrelevant for prediction. So there is some sort of feature selection that will be performed by Gaussian processes when that is the case. And that will help you to make predictions in high dimensional spaces. But if you have like a lot of dimensions, for example, let's say that you have only 100 points and thousands of dimensions, in that case, it's better to use a different model, because even a linear model is too complex in that setting. Because typically what you will have to do is to introduce some sort of regularization or something else to somehow limit the flexibility of your model. Because using a linear model in that setting is probably going to lead to overfitting.